Alright, let's start talking about kinematic equations. The prefix kin, K-I-N, means to move, alright? So these are the equations of motion. And I call them UAM equations. They are uniformly accelerated motion equations. So they are only true if the acceleration is constant or uniform, okay? Now, we've already discussed a couple of these UAM equations before, so let's go ahead and write down what we already know. We know that the velocity is equal to the displacement over the change in time, okay? And we know that the acceleration is equal to the change in velocity over the change in time. Alright, so these two equations can be manipulated to give us the other equations for motion. So let's look at this second equation here. Alright, we can go ahead and expand that and say that delta V is final minus initial. And so we can plug that in here. So we get acceleration equals final velocity minus initial velocity over the change in time. Let's multiply both sides by change in time. Those go away. We get delta t times acceleration equals final velocity minus initial velocity. Let's add the initial velocity to both sides, and we get that the final velocity equals the initial velocity plus acceleration times time. Alright, that is another one of our kinematic equations. You are responsible for memorizing all of these, by the way. We have this one, and we have this one. This one we're not going to call a UAM equation because the acceleration could be changing here. Now, as I have it written, this is an instantaneous acceleration and it could be used, but you know, we have seen it where we've got the line over the top, and that's the average acceleration, which means that it was changing throughout the motion. So we kind of don't use that one so much. Alright, let's look at our next equation. In order to do the next equation, we actually need to represent the one that we just found graphically. So we're going to look at an acceleration versus time graph. Okay, and let's say that we have some acceleration here. Alright, remember that I told you, and we'll go out to some time here, I told you that the area under an acceleration versus time graph was equal to the velocity, the change in velocity. Okay, so that means that the area of that rectangle, base times the height, is actually equal to the base would be the time and the height would be the acceleration. So time times acceleration, which means, and if that's all equal to delta V, then that means that delta V is equal to acceleration times time. Okay, well, we know that delta V is, let me just move up here, we know that delta means change, so delta V is equal to the final minus the initial. So let's kind of put that in there. Final minus initial is equal to acceleration times time. And then we will add our initial velocity to both sides. So the final velocity equals initial velocity plus acceleration times time, which is exactly what we solved for over here. So that just graphically shows you also that we get the same exact equation. Alright, let's get the next equation. Let's say that we have a velocity versus time graph and we have some motion graphed here. And we're going to go ahead and call this point our initial velocity. Alright, and we'll call this 0 down here. So our initial velocity was something greater than 0 to begin with. And we'll say that this is our final velocity up here. Alright, well, remember I told you that the area under the line on a velocity versus time graph was equal to the change in position. Okay, well, you'll notice that this is an unusual shape. This is a trapezoid, so I can't really do anything with it unless I split it right here. And if I do that, then I get a triangle and a rectangle. So this can be the change in position 1. This down here can be the change in position 2. So the total change in position is going to be equal to delta x1 plus delta x2. Alright, so we'll write that over here. Okay, so let's see here. We know that we have area of a rectangle is the base times the height. Alright, so the base is going to be time, and the height is going to be our velocity there. So we get the base is time, and the height is the initial velocity. Alright, so delta x2 is equal to v naught t. This little 0 here, that's said or spoken v naught, and that just means the initial velocity. You could also use v sub I, but I like v naught. Alright, now let's look at the triangle up here. We know that the area of a triangle is equal to 1/2 the base times the height. So we're going to get 1/2. Now the base is time times, now the height is this right here, and that's going to be from the final velocity to the initial velocity. Alright, so to get that change there in that distance, we have to subtract. So that's going to be v final minus v initial. Okay? Alright, well, looking at this v final minus v initial, we can say that that's delta v. Alright, so we have the total displacement is equal to the delta x1 plus delta x2, which gives us the delta x1 we just calculated or just figured out was this up here. So that's going to be the 1/2 t times delta v plus v naught t. Alright, well, if we look at that delta v right there, we can go back and look at that acceleration versus time graph that we made earlier, and remember that the area under that was equal to the change in velocity. So, and we said that the area of that rectangle was the base times the height, alright, and that was equal to the change in velocity. So we can plug in AT right here. So we get that delta x equals 1/2 t times AT plus V naught t. Okay, so looking at this term, we've got two t's in there. So we get delta x equals 1/2 AT squared plus V naught t. Now the way that we actually write this final equation, we put this in front. So delta x is equal to V naught t plus 1/2 AT squared. And that is your third kinematic equation that you need to memorize. Alright, to get our last kinematic equation, we have to use the previous two that we found. Let's resolve this equation for time. Okay, you would subtract the initial velocity to the other side, so you would have the negative VO, and so that would be the V final minus the V initial, and you would divide this side by A over here. So we have that. So time equals V final minus V initial divided by acceleration. We can take that and we can put this value here in for the t's in this equation. Alright, so let's write that. We've got delta x equals V naught times V final minus V initial over acceleration plus 1/2 acceleration times V final minus V initial over acceleration times V final minus V initial over acceleration, because that t is squared. Alright, now I notice that I have an acceleration here in the numerator, so I can cancel out with one of the accelerations in the denominator. And then I notice that I have an acceleration here and here, so let's multiply both sides by acceleration. Okay, so that means that cancels out both of those, and we get acceleration times delta x equals V naught times V final minus V initial plus 1/2 V final minus V initial times V final minus V initial. Okay? So we can go ahead and simplify this just a little bit. I'm going to go through this part really quickly. When we get to these two, that's just squared because it's multiplied by itself. So let's just go ahead and write it as being squared for now. Alright, I want to get rid of this 1/2 because it's bugging me, so I'm going to multiply both sides by 2. So that will cancel out the 2's on this side. So we've got 2 times the acceleration times delta x equals V naught times V final minus V initial plus V final minus V initial squared. Okay, now we can go ahead and do the distributing in here. This is a polynomial, so let's go ahead and write it like that. So we've got 2 times the acceleration times delta x equals V naught times V final minus V initial plus, okay, so this is that FOIL thing that we have to do. So we get V final squared minus 2 v final v naught plus v naught squared. Alright, and hopefully you don't need me to walk you through foiling that stuff. Alright, so if we look here, we see that we have some more simplifying to do, so let's go ahead and do that. 2 times acceleration times delta x equals 2 v final v naught minus 2 v naught squared plus v final squared minus 2 v final v naught plus v naught squared. Okay? Now let's go ahead and combine like terms. We've got a positive 2 v final v naught. We've got a negative 2 v final v naught. So those cancel out. And then I notice that we have a negative 2 v naught squared and a positive v naught squared. So this positive one can cancel with one of those over there. So then that gives us 2 times the acceleration times delta x is equal to negative v naught squared plus v final squared. And let's get some more space here. And then we can go ahead and add the v naught squared to both sides. So you get v final squared is equal to v initial squared plus 2a times delta x. Alright, and this is your fourth and final kinematic equation that you need to memorize. Alright, and we saw all of those represented graphically. Now there's something interesting about each of these kinematic equations. Alright, these kinematic equations allow you to solve for things that you don't know. Alright, so notice in the first kinematic equation we don't have acceleration. Alright, there are 5 kinematic variables. There's v final, there's v initial, there is displacement, there is acceleration, and there's time. Okay? If you know 3 of the variables, then you can solve for the other 2. And it could be any combination of those. Alright? So there are 5 kinematic variables. There are 4 kinematic equations. If you know 3 of the variables, you can solve for the other 2, which leaves you with one happy physics student. Alright? Look at equation number 2. It doesn't have anything to do with displacement. So if you're given a problem and they don't tell you anything about displacement, this would be a really good equation to use. If you're given a problem and they don't tell you anything about acceleration, this one could be used. If you are given a problem, let's look at number 3 here. Which one is this missing? V final. So if you're not given anything about the final velocity, you could use this one. If let's look at this last one down here. It doesn't have time. So if you are given an equation or you're given information and time is not given to you, then this equation would be useful. And we're going to do a lot of practice with our kinematic equations, so don't worry. Go ahead and get started on memorizing this. Thank you for learning with me today, and I will see you next time.